Stephen Neshaba, and I'm here to help you out with your the second calculation having to do with the pre-lab of the decomposition of hydrogen peroxide lab that you'll be doing in the first lab of the semester. So here's the objective. Say you have this stoppered 150 ml flask, and it has 25 mils of aqueous solution, and some bubbles of oxygen gas are forming. You've got a pressure sensor on it, and you notice that the pressure is increasing at a rate of 0.01 atmospheres per second. And your task is to translate that increase in pressure to a rate of the reaction. And the operative equations are equations 2 and 3. I'll just highlight these for you. The increase in pressure multiplied by these constants will give us how fast the hydrogen peroxide concentration is going down. Once we have the rate at which the hydrogen peroxide concentration is going down, we'll use equation 2 to get a rate out of that. So let's go back to where we were in the Excel sheet last time. And the first thing I need to do is correct a problem that I had last time. You may have noticed that, well, this is what we had here. Last time I had left these two at 23 mils, and that had produced a volume of the solution of 26 mils in both cases, and that's wrong, so that's why I'm reducing the amount of water in both of those runs 4 and 5, so that the total amount of solution is adds up to 25 mils. So here we go. You may have noticed I've added a few columns here. If you'd like, put a pause and add those columns and fix these volumes. Okay, I assume you're back. I'm going to type in what the pre-lab says is 0.01 atmospheres per second rate of increase in the pressure in the Erlenmeyer flask. Of course, you'll be measuring those values, and it will be whatever you get in the lab. Now, I want to calculate the change in the rate of hydrogen peroxide concentration. And why don't you give that a shot? Pause and give it a shot. Okay, I'm back. I'm going to see if I can do it. I will type in equals, and I know that there's a factor of -2 in front, multiplied by the volume of the air, which was that number, and I'm going to divide by, let's see, I need to divide by several things in the denominator. So divide by, I'll put a parentheses here in the denominator, times R times the temperature times the volume of the solution, which was 25 mils. I'll close parentheses on that. And there we go. And let's see, I do want to do one more fix right off the bat here, because these are constants, just as we did before. I want to make those relative addressing in case I want to do some fill down later, and you probably will. So I'll change that to $B, number, etc. So there we have that. Now I notice that this is a negative number that's coming out. That's fine. That's because the hydrogen peroxide is disappearing. So I have one more equation to do, and how about you try that? You'll go back and look at equation 2 and implement this conversion factor right here. Give it a pause and try it. Okay, we're back, and I'm going to do this. I see all I need to do is multiply by -1/2 to get the rate out of it. So here we're going to do that equals -1/2 times the rate disappearance of hydrogen peroxide, which we just calculated. And there we go. So now we notice that we get a positive number for the reaction rate. That's good too. Reaction rates generally are defined such that we get a positive number. And that's the end of the pre-lab. That's the numbers. These are the numbers that we're asking you to get. We also want you to be able to get them for any of these other rows, but because of your other runs, you'll want to get a reaction rate. But that's going to be easy because we've set this all up so that you can do things like a fill down, go down here if you remember, and drag down.